Yes, sir.
Renal function. This is our second to last chapter for your test material. Again, next week we will cover chapter 4. We'll have our first lab next week, and I'll give you a review for your exam.
Okay.
So,
Isn't it H?
for which one?
Oh, it's a nephron.
Oh, it's nephron.
That's how you spell nephron.
What?
God.
I did not use it.
What happened?
Nephron, that's what I call it.
Nephron's on you, watch her.
So you're gonna talk about the nephron.
The age, I say.
Sorry to
I
interrupt.
don't have spell check.
Smells like
Nephron. The good thing about this is you guys have already been tested on this in intro. You've already labeled it in intro, and hopefully if you did it then, because this is on the test again. This will be on your first test, the nephron, we'll talk about it. We're gonna go a little more in depth today than we did in the intro class. I mean, I'm not trying to make it harder than it is, but for whatever reason, the registry likes to ask questions about the nephron. So I wanna make sure that you guys are prepared for that.
I don't know if I can draw that.
Because if you really think about it, this will be the last time we go over this before you take the registry, okay? I mean, because after this, we'll cover new stuff, we'll go to clinicals, other than doing review sessions and stuff. So kind of understand a little bit about what we're talking about today. All right, this chapter starts on page 39 going into 40. Again, if I pulled up in D2L, I can show you a lot better picture of the nephron. We're going to be talking about page 41 today a lot, because that's where the picture is of it. But I don't want you to lose sight of the forest here, okay? Everything we're fixing to talk about involves the human body. We're going to touch on the A and P part, where you've got 2 kidneys, 2 ureters, a bladder, and a urethra, okay? That is the excretory system for urine production. That's the whole thing. You got to have all that. As you guys know, you can live with 1 kidney. If you can live with 1 kidney, that must mean that if you have a little bit of trouble with your kidneys, the other one can work double time, right? Or else you wouldn't be able to just live with 1 kidney, okay? So understand that, because we're going to be talking about all the damage that can be done and all of these types of filtration systems and all of that. But do understand that you have like 1.5 million nephrons in each kidney. So naturally, if you have damage to some nephrons, other ones kind of keep up the pace to make sure, you know. But the problem with it is by the time you become symptomatic, you probably have quite a bit of kidney damage, right? Because if other ones work double time to make up for ones that aren't working, by the time you start feeling it, then you probably got kidney damage. Okay, one of your objectives, the first thing is just saying how many actual nephrons are in each kidney. On page 40 under renal physiology, it says each kidney contains approximately 1 to 1.5 millions of functional units called nephrons. The very definition for a nephron is it's the functional unit of the kidney. Now, another objective states that you need to be able to trace the renal blood flow through the kidney. Now, this is where we're going to kind of build on what we covered in the intro class. This is not renal blood flow, okay? This is urine, or what they call glomerular filtrate flow, right? So that used to confuse me, because the instructor I had, I mean, it was my own fault, but I used to think, well, hold it, I'm getting this mixed up. This is the flow of what will become urine, okay? But if I talk about renal blood flow, I'm talking about like as blood enters the nephron, it comes in through what's called the afferent arteriole. That's listed on that picture, okay? And I'm gonna say this slow so we can all get it. Blood is supplied to the kidney via the renal artery, okay? That branches off into what's called afferent arterioles. That's what's going to enter the kidney. Remember, we're talking about a nephron here. You got 1.5 million of these. There's not one just big nephron in each kidney. Okay, you got lots of these. So if there's damage, probably you're not going to feel it. So here we got blood entering the nephron. It's coming up this tubule. right here, you guys remember, I didn't label it, but this is called the glomerulus, right? Remember I told you guys to think of the glomerulus as like a sponge. Certain things in the blood are allowed to go through the glomerulus, certain things aren't, okay? So let's talk about some of the things. Hopefully this just makes common sense. Naturally, if it's like a sponge, larger things can't go through it, okay? When we're talking about the world of blood, larger things, even though we can't see it, are things like large proteins, cells, anything like that. You don't see blood in your urine, or you shouldn't, right, normally?
Right.
So it's because plasma proteins, red blood cells, white blood cells, none of those things should be passing through the glomerulus, so they stay in the blood, right? That's all the kidneys do, is they're cleaning the blood. That's the major function of the kidneys. They clean the blood. If the kidneys aren't working, you have to go to dialysis, and the dialysis cleans the blood, right?
Mhm.
Okay, so again, I have red.
I got a good one.
You got a good red one?
Yeah.
For the board?
Huh?
For the board?
Yeah.
Carry a red one for the board in your purse.
My first.
All right. I
Her,
got red
her
in there.
backpack.
Well, when I go to study rooms,
Oh, okay. All right. Well, good deal.
I got stolen from here.
No, I didn't mean that. That's just, I don't know that I. All right, let's do it like that, and, maybe that'll help us. I'm gonna hold on to it just a minute longer, okay? Okay, so anyway, here comes your blood supply. Again, if it goes through the sponge or the glomerulus, now, once it gets into here, it is on its way to becoming urine, okay? Now, where we're gonna go a little bit more in depth today is I'm not trying to mess up the picture, guys, but I'm fixing to scribble on it.
Okay. It's all the capillary.
Afferent arteriole goes through the glomerulus. If it doesn't go through the glomerulus, it keeps going through the efferent arteriole. Right now, we're talking about renal blood flow, all right? Now, from the efferent arteriole, what it's gonna do is it's gonna do this. Okay, this is like little capillaries that are going to surround the nephron, okay? And even though I just screwed it all up, the reason I'm putting it there is because this is where certain exchanges are gonna happen. There's some things that are in the filtrate that have to go back into the blood. There's certain things that bypass the glomerulus that are in the blood that we gotta get rid of it, like a medication that a doctor gives you, right? So there is a process to where things go from the filtrate into the blood, and another process where things go from the blood into the filtrate. Two major words you gotta know the difference in: reabsorption and secretion. There's a great picture in your book. I'll show it to you. It's also on the PowerPoint, and you need to make sure that you understand that concept, okay? I'm not keeping up, because I've got some. I'm just too lazy to walk in the other room.
Well, I always have them, just in case you ever need.
So I want you guys to write this down. It's in your book, and I'll show you where, but there's gonna be a test question on renal blood flow, and I want you guys to understand what I'm talking about. So I'm gonna write it on the board, so you'll have no excuse if you didn't see it. Renal blood flow. Okay, we're gonna start off with the afferent arteriole. I may be spelling this wrong, but bear with me. Okay, afferent arteriole. It goes through the glomerulus, okay? But I'm not including the glomerulus because the glomerulus is technically part of the nephron, okay?
Right.
Goes through the glomerulus, now it comes out the efferent arteriole. Okay? Then there's gonna be something that goes through, and it'll show you a picture of this in your book, called the peritubular capillaries, okay? I guess I'll just say the renal vein after that. Okay, that's the renal blood flow. So here we go. Comes through the afferent arteriole, may or may not go through the glomerulus. Then it goes back out the efferent arteriole. If it didn't go through the glomerulus, then it goes through, these are called like the peritubular capillaries on top. Once you get toward the bottom, it's called the vasa recta, okay? That's the blood flow or the capillary flow with and around the nephron. Now, if I told you to tell me, okay, tell me in order the glomerular filtrate, okay, you would tell me, okay, anything that sifts through the glomerulus, anything that goes through the spine, it's gonna go through Bowman's capsule, and it's gonna go through the proximal convoluted tubule, then it's gonna make its way through the descending and the ascending loop of Henle, it's gonna go over the distal convoluted tubule, and then it's gonna go down into the collecting duct. All the collecting ducts basically drain into the ureter. Okay, that makes sense to everybody? Under glomerular filtration on page 41, just so you understand, as far as on the test, it'll probably say, if I tell you, you know, what's the function of the glomerulus, it's filtration. It's filtering substance, that's the main function. But it does say on page 41 over in the right-hand column, it says that the glomerulus serves as a non-selective filter of plasma substances with molecular weights less than 70,000. So basically, anything that has a molecular weight less than 70,000, or if it's cellular, like red blood cells, white blood cells, and your larger proteins, it should not go through the glomerulus. You know, that sifts out a lot of things. I mean, that's a lot of things that we should not see in our urine because it doesn't go through the glomerulus. But there's so many other substances that do get sifted out through the glomerulus and end up getting in that filtrate tract. One of them, glucose. All of our glucose gets filtered. Every bit of it should get filtered. But you can't lose all the glucose in your urine, right? I mean, you gotta have glucose in your blood to give you energy. Glucose gives our bodies energy. But I'm sitting here telling you, all of the glucose in your blood goes through this glomerulus and gets in this tubule. Now we gotta get it out of the tubule, okay? It goes through the tubule, we gotta get it back out and get it into this blood supply, okay? Because we need to have it.
Question.
Yeah.
So this glucose is getting into the nephron because it's going through the glomerulus. It's going through the glomerulus because it's small enough to?
Right.
Okay, thank you.
All of it, every bit of it, glucose, amino acids, salts, sodium chloride, it all goes through the glomerulus.
Sure. Oh, no, I mean, I've got it. Okay.
All right, I want to explain something. I'm not right here in the book, but this is just a real good time to do it. Okay, so like I told, and I think I did the same picture in the intro class, but it's so, I'm gonna do it again because it's important. If all of those glucose molecules go through, okay, let's just say this is a normal person. Let's say that's dissolved glucose molecules that went through the glomerulus, okay? They made it through. A normal person right here, if you don't have any type of kidney problems, all of those glucose molecules are going to be reabsorbed back into the blood. Reabsorbed means all of these glucose molecules are going to go back into that little peritubular capillary right there. Okay? Now we have our energy back. The problem is that if we have a patient that is a diabetic, and let's just say this is the normal amount of glucose. Now let's just say that now we're dealing with a diabetic and they have, I mean, I could keep going forever. They got too much glucose that got filtered, right? So it breaks what's called the renal threshold. And even though the body tries to reabsorb as much of that glucose as it can, there's so much that they call it spilling over into the urine that some of it makes its way on down. Okay, it didn't get reabsorbed in the proximal convoluted tubule. Okay, it reabsorbed as much as it could. Like, look, like you see how much made it through. Okay, which means it reabsorbed a lot, but it couldn't reabsorb it all. All right, everybody with me? Everybody understand that concept there?
So now that the threshold has been reached and now glycose is headed towards the bladder, we've got glycosuria.
Yep. So that's one reason, if you ever have glucose in your urine, that is not good, okay? Because it means something is going on to where you had so much glucose in your blood or in your plasma that it's so much that the kidneys can't compensate for it all right there, okay? And because of that, now this is the part I need you to understand. If at all times your body is that much glucose is being presented to all these tubules in your nephron, in other words, it's having to work its tail off, okay? Because it's not just a regular amount of glucose. At all times, it's having to reabsorb and it's going, I can't do it, I can't do it, I'm trying my hardest. It's kind of like your heart, right? If your heart's having to pump really, really hard over an extended amount of time, you're gonna go into congestive heart failure, right? Because it can't just do that forever. And that's how come diabetics, they tell them, like, you better eat right, you better do what the doctor tells you, because if you don't, you're going to eventually possibly have kidney troubles, okay? Because so much glucose is being presented to all those nephrons over an extended period of time, all right? That's how come they generally, unfortunately, sometimes have kidney trouble.
That result in renal failure?
Yeah, or it results in going on dialysis later on in life.
Yeah, your veins don't do very well with glucose levels.
Before we go any further, I'm gonna skip ahead because it's too important. Page 45, turn to page 45, I'll go back, we'll catch up. I want you to look at that block on page 45. Don't look at that picture up above it. We'll get to that sometime, okay? I just want you to look at that little picture, figure 3, tag 7. All you're looking at right there is Bowman's capsule with the glomerulus in it. You guys follow me? Okay, you got the afferent arteriole coming in and the efferent arteriole. Look at those two lines right there. Put an asterisk, but I need you to understand that concept. If you take a substance from the tubule, okay, and see how the arrow's going into the blood, that's called reabsorption. Secretion is when you take a substance that did not get filtered through the glomerulus. It stayed in the blood supply, but it's got to get back. In other words, the body needs to get rid of it as urine. So some substances go from the blood to the filtrate, okay, or to the little urine tubule, and that's called secretion. You gotta know the difference between those two because it's a real important concept, all right? Okay, the next thing I want to talk about is part of, other than the size of particles, like I'm sitting up here telling you, okay, little things are allowed to go through this glomerulus, and certain things don't go through the glomerulus, like plasma proteins and your red cells and stuff. But this glomerulus only works properly if it has the perfect blood pressure. I want you to think of this as like two water hoses, right? One water hose is going in, one water hose is going out. But that pressure has to be maintained at the perfect environment. But people don't always have good blood pressure, do they? Some people have real high blood pressure and some people have low blood pressure. But you know what? That can't affect this. The body has to have a way to compensate. If somebody, for example, has a drop in blood pressure, in other words, all their blood pressure drops, but how are we going to keep the pressure of blood going into this glomerulus if they have low blood pressure, right? What happens is this afferent arteriole gets wider, okay? It widens up, and the efferent arteriole tightens up, it constricts. In other words, it's going to compensate for the blood pressure to where there's always the perfect, or should be the perfect amount of pressure to send water through this sponge, okay? If I lay a sponge right here in my hand and I shoot a water hose of water going through it, if I do it real high, right, there's going to be like a certain amount going through. But if I change it and make it where not much water pressure is hitting it, do you agree less things are going to go through because I'm not putting enough pressure on it? Right. So the body has to compensate for that. There is a system that helps the body regulate this. It's called the renin-angiotensin-aldosterone system. You don't have to say it, don't have to spell it, it's got an abbreviation, the RAAS system. And this should be on your book on page 42, the right-hand column. So the renin-angiotensin-aldosterone system is usually activated when somebody's blood pressure drops. So instead of reading this paragraph on page 42, I think it's better understandable if you'll look at page 43, look at that blue box, table 3, tac 1. This is what happens in the renin-angiotensin-aldosterone system. It says dilation of the afferent arteriole and contraction of the efferent arteriole take place. This stimulates sodium reabsorption in the proximal convoluted tubule. This triggers the adrenal cortex to release sodium-retaining hormone aldosterone, which causes the reabsorption of sodium and potassium excretion in the distal convoluted tubule and the collecting duct. It triggers antidiuretic hormone, or ADH, that's better known as vasopressin, released by the hypothalamus to stimulate water reabsorption in the collecting duct. Okay, that's really complicated, but this is what I want you to remember. Do you guys agree that where sodium goes, water usually follows?
Yep.
Okay, so someone that has high blood pressure, how many of you have ever been talking to somebody before and they're having congestive heart failure and they have high blood pressure and their doctor tells them, like, look, you need to lay off the sodium, right? They tell them to lay off the sodium because think about it. If they have a lot of sodium in their blood, they've already got high blood pressure. If there's a lot of sodium in their blood, that's going to bring water in, right? That causes more pressure in the blood. So you want to stay away from sodium. What this RAS system, or the RAAS system does is if you have a low blood pressure, you want sodium in your blood. Do you agree? Because look, you don't have much pressure. So if you don't have any pressure in your hose, you need more water in the hose. Well, the quickest way to get more water in the hose is flood that hose with sodium and the water will follow, okay? So that's what this system does in a nutshell. It has to do with blood pressure and it has to do with sodium retention to increase the blood pressure so we have the proper environment so the right things will sift through this glomerulus, okay? I made that as simple as I can make it for you, okay? Now, when you read about that in your book, it's going to throw in a couple other words like angiotensin 1 and angiotensin 2, but I'm telling you what I think you need to know to where you'll get it on the register, okay? The RAAS system has to do with sodium retention to increase the blood pressure, all right, so that glomerulus will work properly. It has to do with the blood supply in the glomerulus. And when you're reading that, if you don't understand it, the best thing I can tell you to help you understand it is think sodium retention and increasing the blood pressure. That's the two keys of that system. Okay, reabsorption mechanisms on page 43 at the bottom. You guys see those two terms there? One's called active transport, one's called passive transport. Everybody see that? Mm-hmm. Okay, here's what I want you to know about active transport. For active transport to occur, whatever substance is being transported, it has to combine with a carrier protein, okay? For example, glucose. All this glucose that I drew up on the board, for it to be reabsorbed in the blood, it combines with a carrier protein. Glucose, amino acids, salts, those are all examples of things that use active transport. And it says that word for word in your book, okay? It's going to say glucose, amino acids, and salts are examples of active transport. Certain things use passive transport. Passive transport has to do with things crossing a membrane due to certain pressures, okay? The biggest example I can tell you, if I was to ask you on the test, give me an example of something that uses passive transport, is water. Water is passively transported all throughout the nephron. There is only one place in the nephron where water is not passively transported, okay? And it's right here in what's called the ascending loop of Henle. The ascending loop of Henle is impermeable to water, and water is not allowed to cross, okay? It is not allowed to do it right here, okay? And it tells you this in your book, guys. I mean, everything I'm telling you, it's on your PowerPoint and it's in your book. Water is passively reabsorbed all throughout the nephron except right here. It's big time right in this area, okay?
What was it that you said, for glucose to be reabsorbed, it must combine with what?
A carrier molecule or a carrier protein. Okay, as far as if you need to know in your book, guys, page 44 in the left-hand column, that's where it talks about these examples of active transport and passive transport. Like the very first 20 lines on page 44 talks about all of that in detail. All right, I want to talk about collecting duct concentration. This is on page 44. The last, in the right-hand column, that last section, it says collecting duct concentration. So what we're talking about right now, guys, is right here in the collecting duct, from the distal convoluted tubule to the collecting duct, all right? We have got to determine, believe it or not, we can make this all complicated, but a big part of whether your body voids out urine or retains water has to do with your hydration status. It's that simple, okay? There's a mechanism in your body that's triggered in your brain, the hypothalamus and the pituitary, that, for example, when you're thirsty or when the body is telling itself, I need to retain water, it triggers something called antidiuretic hormone, better known as vasopressin, okay? And most people, this works like clockwork. And it's, again, I mean, this is a huge ordeal because it's telling your body, hey, I need to retain all my water or I'm fixing to pass out. My electrolytes are gonna go crazy. And that's how come if you're not drinking fluid, you're not voiding urine, okay? And if you're drinking lots of fluid, you're voiding lots of urine. All right, so let's talk about this. It says the final concentration of the filtrate through the reabsorption of water begins in the late distal tubule and continues into the collecting duct. It says reabsorption depends on the osmotic gradient in the medulla and the hormone vasopressin. Again, that's what they're talking about when they say antidiuretic hormone. Now skip about 8 lines and it says a high level of ADH increases the permeability, resulting in increased reabsorption of water and a low volume concentrated urine. We'll skip another sentence. It says, just as the production of aldosterone is controlled by the body's sodium concentration, that's that RAAS system. It says production of antidiuretic hormone is determined by the state of the body's hydration. Make sure you understand that sentence right there. ADH is produced by the hydration status of the body. That black bold at the very bottom of the page is very important. It says, it says an increase in body hydration means that your body does not produce ADH, or it doesn't produce as much, which means you have an increased urine volume, okay? So if your body produces, I mean, think about the word. That's how I remember it. Like if I start getting confused on this and I go, hold it, I'm getting mixed up. I think about the word, I go, antidiuretic hormone. What does the word diuretic mean? Anybody? Means you're going to void off urine, right?
Right.
If you have congestive heart failure, they're going to give you Lasix or some sort of antidiuretic to void off lots of fluid, right? Lots of urine. That's what a diuretic does. An antidiuretic doesn't want you to void off any fluid, all right? It's wanting the body to retain the water. So when your ADH is turned on, in other words, when the body is stimulated and your body is telling itself you need to retain all the water you can, it actually turns on antidiuretic hormone. So an increase in antidiuretic hormone means a decrease in urine production, right? If your body needs to hold what little water it has in it, you don't want to be voiding urine very often, right? And the urine that you do void is not gonna have quite as much water in it, so it's gonna be more concentrated, which is what makes it a darker yellow color. I'm not telling you to do it this weekend, but if you're out mowing or doing something strenuous activity, running or whatever, if you don't drink fluids, I will almost guarantee you that when you void urine, that urine is gonna be darker than normal, okay, and it won't be quite as much. So understand those two little sentences at the very bottom of page 44. All right, I got 10 o'clock, so let's take a break. Let's take,